Hi, I am Dailen Brown, a PhD candidate in the Mechanical Engineering Department at Penn State University. I will be presenting the design and evaluation of an incremental needle insertion system, which will be used to collect force and position data in future cadaver experiments. In the medical field, simulation plays an increasingly pivotal role in training. Medical simulation has grown over the years because it is safer and easier to work with. This can be very important in training residents how to perform high-risk operations such as central venous catheterization, often referred to as CVC. There are around 5 million CVCs performed each year, many of which involve complications such as infection, arterial puncture, and collapsed lung. The Dynamic Haptic Robotic Trainer, or DHRT, pictured here, was developed by the Precision Medical Instrument Design Lab at Penn State and uses a haptic robotic arm to provide real-time force feedback to simulate the feel of performing a CVC, allowing users to practice CVC insertions on virtual patients of varying age, weight, and anatomy. Ultrasound plays a vital role in performing a CVC by providing visual feedback during needle insertion. The current ultrasound simulation deployed on the DHRT is impressive in its appearance, but it's unable to accurately simulate real ultrasound images. In order to improve this, we are interested in studying the interaction between needle forces and ultrasound tissue motion as they relate to CVC. In order to observe these interactions, a new device was designed and manufactured for use in cadaver studies. This new device is known as the Incremental Needle Insertion System. The purpose of this device is to insert a needle into a cadaver in a straight line at increments of 5 millimeters while simultaneously recording position and taking force measurements. By recording ultrasound images between increments of insertion, we can compare the state of the tissue from one increment to the next with the forces applied by the needle. This allows us to map the needle-tissue interactions and then use that map to generate more realistic tissue motion simulations. The system, pictured here, uses a 6-axis force transducer to record the forces involved in insertion and an electromagnetic probe to track position. It has a lead screw and a telescoping tube allowing for 5 millimeters of translation for every full knob rotation. An extension spring keeps the needle in place between movements, and a Jacobs chuck allows for versatility in needle sizes. The device is mounted to an articulating arm, which allows the device to be easily positioned to various insertion sites while keeping the device in place during insertion. The system was deployed in a cadaver experiment to test its ability to sense force and position in a straight line insertion. 5 needle insertions were performed in 2 subgroups. These subgroups consisted of 2 incremental insertions with pauses for ultrasound study and 3 full insertions where the knob was continuously rotated to plunge the needle to a 30 millimeter depth without any pausing. Force and position was recorded during needle advancement for all 5 trials. After data collection was performed, the device was evaluated for its ability to perform a straight line insertion with minimal deviation. This was done by generating a parameterized equation based on the recorded orientation of the system at the start of insertion, projecting an expected straight line path of travel. Then, the deviation from each data point from this projected needle path was calculated using MATLAB. Force data was not analyzed for this paper because the transducer used in this insertion system is the same as was used in previous studies in our lab and has already been shown to produce accurate results. It should be noted, however, that the maximum axial force was similar between the full and incremental insertions and was comparable to previous studies. Pictured right is the measured needle position and projected insertion path for one of the 5 trials. It is clear from this figure that there are significant deviations from the path, but the overall trajectory remains the same. The average measured deviation across all 5 insertions was 1.6 millimeters. These deviations are most likely caused by unwanted movement in the articulating arm joints and small translational movements in the telescoping tube as the lead screw is advanced. The plot on the left shows the average deviations across the first and second subgroups. The error bars signify statistical variance in the data. Although the average deviation is not extremely different between the two, the incremental insertions did have a higher deviation as well as a significantly larger variance. This is expected because the device comes in and out of contact with human hands multiple times during the trial, whereas the full insertions only had one continuous contact. Despite these deviations, it was determined that the device is suitable for our needs because the average deviation is sufficiently low. The natural tremor of human hands, which increases with fatigue, has been shown in literature to produce similar or higher deviations during straight line insertion. Thank you for watching this presentation. I would like to recognize NIH for generously supporting this work. I would also like to thank my co-authors and the staff of Hershey Medical Center for their help and use of their facilities. Co-authors Dr. Moore and Miller own equity in Medulate, which may have future interest in this project. Company ownership has been reviewed by the university's Individual Conflict of Interest Committee and is currently being managed by the university.